So the outputs have been dealt with, right? So we want to look at the inputs and how they generate those step numbers for us. Okay. So what we're going to do is we'll use the diagram as well over here just to help us. Okay. So remember, this is rest. Okay, we're assuming there's nothing in here, the sensor isn't activated, no one has pressed the start button, and we'll assume the cylinder is retracted, so the sensor is on. Okay, everything is at rest. So what we want to do is we expect, well, someone's going to put a part in here, so either metal or plastic. That sensor is going to be on now for both of them. Okay, only this sensor works with the metal, but this sensor will detect either metal or plastic. So something like a capacitive sensor or something like that. Proximity sensor, anything along those lines. So we're going to assume, right, someone's going to put a puck in here, they're going to press the start button, and then that's going to happen. Okay, that's going to move forward. So that's what we're looking to achieve. So essentially, we're going to have 3 inputs that are going to come along here. So we're going to say we want the start button pressed, we want to make sure that there's a part in the sensor, and we want to make sure that our cylinder is retracted pretty much. Okay, and then once those things happen, we're going to go ahead and move the value 10 into so we need to use a move command. Where are our move commands? There it is. We need to do a move, and what we're going to do is we're going to move the value 10 into that data block, okay, and into that position variable, because that will basically then put 10 in, and then we'll see, oh, 10 is in, so extend the cylinder, 10 is in, yeah, turn on the motor. Okay, so that's the way that works. That's the link between, the step numbers are the link between the inputs to the outputs. Now what I also like to do is I like to just say, well, make sure, you know, we're in step 0 first, because if for some reason that someone tried to load the system again, if we didn't have this part in, so we left that out, and someone put another sensor in and the cylinder was retracted, we press start, it would feed another part in, but essentially I want to wait, I only want to do one puck at a time. I want to put the puck in, wait for it to finish and everything to come to rest again, and then for me to push the start button and it to start again. Okay, so that's why we say only allow this line to happen when we're at the start, when we're at rest. Okay, and then you also need a way to get back to rest, and that comes from your stop button. So you've got to have your stop button here. Basically we're going to say when we press the stop button, we're going to move the value 0 in. Okay, now I'm just assuming my stop button is normally open. I'm not going to worry too much about any of that for this example. Okay, but if your stop button was wired normally closed, you would have it like this. Okay, and notice that I don't put any limitation to what step number we have to be in, because at any stage if I press the stop button, I want it to override everything and move 0 into so put the system into rest. So that's why we don't have anything like that before it. Right, brilliant. So that's the start, right? So imagine everything is at rest, we've put a part in, doesn't matter what it is, we've pressed start and the cylinder pushes it forward. So we said the motor has come on, it's latched on, and the cylinder has moved forward. So I need the cylinder then to come back automatically. So basically I want to say, well, I want to make sure it gets a full extension, so it goes right up, gets its max proximity sensor, and then it automatically returns. So what I want to do is basically, we've gone into step 10. So we're in step 10, and then once we just check that we get to A fully extended, which is told by my A1 sensor, then I want to go ahead and move into step 20. Okay, so therefore it doesn't matter how long or how quick it takes for my cylinder to move forward, it won't go into the next step until it sees it's hit A1. So it doesn't matter, this is A1, this is A0, doesn't matter how long it takes for me to get there, as soon as it gets there, it will go into step 20. will move to step 20, and then we know in step 20 A will retract because A is no longer extending because we're not in step 10 anymore. So that's the real benefit of this as well. You're not using any timing sequences or anything. So especially when you have two sensors there tell you position, there's no reason to try and use a timer to see how long or how short that should come out. We want a full extension of the cylinder, and that's the way we do it. So we've done this. We've generated the inputs for step 10, motors turn on, A's come out, generate the inputs to trigger step 20, and that's just basically checking that this has fully extended, and then we've put it retracted. Okay. So going from step 20 into step 30 is the interesting one for us because it's going to be different from here to here. So what we're going to do is we're just going to deal with this one first. This is the busiest one, the most fullest. So we're going to pretend it's a metal part that's in, or a metal part that was loaded at the start, and we're going to deal with this going forward. Okay. So the next step, we've gone into step 20. Okay, so we're in step 20 now, and we're going to say if this inductive sensor, where's my image? So we're going to say if this inductive sensor is triggered, so imagine that metal part has come in, it's been moving along, the inductive sensor gets triggered, then we're going to go ahead into step 30. So put the input in. This is the input that represents the change in scenarios, and then we're going to move to step 30. So now we're in step 30, and the deflector will come down and it will stay latched down. Okay, and this is where it gets a little bit interesting as well, because we've no sensor to tell me that the inductor or the deflector has come down. So remember the way we have two sensors here, it tells us when it's fully extended, fully retracted. We don't know when this is fully extended or fully retracted. Okay, so what I've got to do here, and this is just to show you, we've got to use a timer, and using the output as a reference. Okay, so just to show you something different. If we could have inputs all the time, that would be probably the most secure. So basically I just want to say, right, well, we're in step 30, and what I want to do is I want to check, has the output come on? So if I actually just put in deflector here, so I'm using the output as an input reference. So remember, that's something like that we've done up here. So we're just basically saying check sorry, I should be in step 30 there. We're saying, is the deflector on? If it is, go ahead and move into step 40. So that'll happen very quickly. As soon as it goes into step 30, it'll fly through that, because at step 30 the deflector should come on. So we'll go through that very, very quickly. Because now we're into step 40, so we're just checking that, basically checking that the deflector has come down, and I want the 2-second delay now before I let it go back up. Okay, so to get that 2-second delay, again we've got to say, right, well, we're in step 40 now, and what I want to do is I want to trigger a timer. Now, I've done many videos on the timers. Unfortunately, just due to this OPC simulation on Fluid Sim, and due to the type PLC I'm using, a very old PLC, the 300s, I've got to use a different timer that you probably haven't seen before and really isn't going to be used a whole lot. But these are the old school somatic timers. So I'm just going to drag one in. Don't worry, I think maybe too much about how it's being used. Be comfortable with the old the newer versions of the timers. But basically what we just got to do is we've got to give the timer a name. Okay, so I call it timer 0. So just define that tag stored in a timer address. That's fine. Okay, you know, the old IEC timers, you know, these ones here would do all this automatically for us. We've got to put in the time delay. So usually we do T hashtag, so we'll say 2 seconds. Okay, but because this is the old semantic ones, we've got to do S5. So the old ones. And the way this timer works basically is at that it starts generating this up for 5 seconds, and then what you do is you use an input symbol and you just call it timer 0. So once this is generated, it will close that input reference, because them two are kind of the same thing, or essentially the same thing. And then what we wanted to do is we wanted to go ahead and move into the next step. Okay, so that will move into step 50. Try not to maybe get too concerned about that, because they're not really hugely used anymore unless you're using very old PLCs. But that's how we do the old school timer. Basically, with the newer ones, all this is just combined into a nice little box. Okay, but that's how we do it. We set the time using the old school reference, and we just make sure the two things are the same reference. So what that will do, that will give me that 2-second delay before I go into step 50. And then we know at step 50, so we move into step 50, we know it's going to break my deflector, so my deflector will come back up and it will break my motor. So essentially that would be the end of my sequence, because the deflector would have came down, the puck would have fell down here. After 2 seconds, the deflector would have came back up and the motor would have turned off. So we're back at rest, but we're still in step 50. So we want to get back to step 0 so that we're able to start the system again. So what we just do is we say, all right, when we're in step 50, just do a wee check for me to make sure, has my motor gone off? So is my motor off? Is my deflector off? And then if that is correct, go ahead and move 0 back in. So that's using that outputs as a reference, because again we've no input that tells us when the motor is on or off, or the deflector is extended or retracted. So we're just looking, is the output on or off? So that's that little trick again, just showing you that how we can use the outputs as inputs for reference. So once we're in 50, is everything turned off? Right, we're back at 0, we're back at rest. So we can go ahead and wait for someone to press the start button, put the sensor in, and go on ahead and do it again. So that covers us for the metal product. Okay, now we just got to do a slight change, or add in a slight bit to show us how to deal with the plastic variation of it. Okay, so we only need to do a slight change, right? And it's basically at line 20, okay? Because line 20 is the key. So currently what we have at line 20 is, well, if we get the inductive sensor, we're going to move into step 30. So if a metal part is coming along here, hit this inductive sensor, we move into step 30 and we finish our sequence. But sometimes we may need to go from step 20 all the way to step 50. Because if we put a plastic puck in, well, this is moving along, we're at step 20, it's not going to get triggered here, it's going to come all the way through, and then the optical sensor is going to trigger it. So basically what we need to say is, we need to say that that's step 20. If we get the inductive sensor, move to step 30. But if we get the optical sensor, move to step 50. So how you do that, and it's basically creating like an OR scenario. Go to where we had step 20, because that's where the magic happens. Right? We already have that in step 20. If we get the inductive sensor, move step 30. I'm just going to copy that. I'm going to say, if we get the optical sensor, move to step 50. Because essentially these two lines are going to happen at the same time. Okay? But only one of them are going to be true. It's either going to be the inductive sensor first, and then that moves to step 30, and therefore this line will be ignored because we'll no longer be in step 20. Or it'll pass the whole way through, it'll stay in step 20, pass the whole way through until we hit the optical sensor. Then it'll go to step 50. We know at step 50 we wanted to cut the the deflector, well, sure, the deflector hasn't turned on, so it doesn't matter, and it will cut the motor, which is what we want. And that is all the inputs to the system. And again, hopefully you can see, I know the inputs aren't really listed here, but you can use this to understand how it works, along with this kind of context of the hardware that you have there. And you know, again, we're just using that. I've gone over many kind of ideas about how we keep our code linear with ladder logic by using these step numbers. And basically the inputs generate the step number, see the way they move the value into that position block, and then the outputs just basically, if you're in that position block, then you trigger the output. So the steps numbers are the link between your inputs and your outputs. And it keeps code nice and linear, you can follow a good pattern, and it's got very good fault finding techniques. So in the kind of final video, we're going to simulate it and watch the solution ultimately happening on FluidSim. Okay, now obviously if you have the hardware, you can just test it straight up, you know, download the code in and see how it tests it. But just to show you some simulation with OPC communication and to show you it working nicely on FluidSim, I'll do that in the next video.